What's your first thought when you think of radioactivity and more specifically the processes of radioactive decay? Maybe scenes like this, or maybe even this. Whatever it is, I'm hopefully going to give you an insight into the real story behind this fascinating phenomenon. Right, let's start right back at the beginning. Think about this. During the early 19th century, radium, a radioactive element, could be found in things such as toothpaste and even chocolate. Crazy, right? This was prior to the discovery by French scientist Henri Becquerel of nuclear radiation in 1896. Whilst working on phosphorescent materials, he noticed that uranium salts would cause blackening of photographic paper, although it soon became clear that this phenomenon had nothing to do with phosphorescence and was better explained by the presence of some form of invisible radiation that caused the plate to react as if it had been exposed to light. Further research by Ernest Rutherford, Marie and Pierre Curie during the late 19th and early 20th century brought about the model of radiation that we understand today. That's the history dealt with, so now let's delve deeper into what radioactive decay really is. In short, radioactive decay is a process in which an unstable nucleus loses energy by emitting ionizing radiation. This radiation comes in many forms. The three most common are alpha, beta and gamma emissions. You may have also heard of a few others, for example electron capture or positron decay. Alpha decay is essentially the process in which an unstable nucleus admits a helium nucleus in a bid to become more stable. Alpha decay is by far the most common form of cluster decay, where the parent nucleus ejects a collection of nucleons, leaving another product behind, like nuclear fission. Like other cluster decays, alpha decay is fundamentally a quantum tunneling process. Quantum tunneling refers to the quantum mechanical phenomenon where a particle tunnels through a barrier that it classically couldn't overcome. Beta-minus decay occurs when a neutron disintegrates into a proton and produces an electron and an electron antineutrino. At the most fundamental level, all that happens is a down quark changes into an up quark. As you can see in the Feynman diagram, hopefully you're familiar with these, the weak nuclear force is mediated by the W- boson. The exchange particle changes the flavour of the quark and takes away the negative one charge, which arises due to the charge difference of the single quarks. As you can probably guess, beta plus decay is the opposite of beta minus decay, so this time a proton changes into a neutron, an up quark changes into a down quark and produces a positron and electron neutrino. This is also known as positron emission. As the charge difference is now positive 1, a W plus boson is formed. Gamma decay is the emission of a gamma photon, which is a package of energy, usually after the occurrence of another nuclear decay process. The daughter nucleus formed is usually left in an excited state and therefore has excess energy. To get rid of this extra energy, it emits a gamma photon and therefore decays to a lower nuclear energy level. Electron capture is the process in which an inner orbiting electron is absorbed into a proton-rich nucleus, thereby changing a proton into a neutron and simultaneously emitting an electron neutrino. The atom is left in an excited state as it has lost an inner electron and so therefore emits an X-ray photon. This decay is a weak nuclear force interaction. As before in beta plus decay, a W plus boson is the exchange particle. Phew, there you go, a brief explanation of the few of the most common types of radioactive decay all in 3 minutes. Thank you for listening.